Have you ever wondered how Einstein, one of the most brilliant minds of the 20th century, developed his groundbreaking theories? This is a question that has sparked intrigue in many of us. Today, we dive into the fascinating world of Einstein's thought experiments, a tool that played a pivotal role in his revolutionary contributions to physics. These mental models provided profound insights, reshaping our understanding of the universe in ways that continue to influence modern physics. Ready to embark on a journey into Einstein's mind? Buckle up, and don't forget to subscribe for more interesting facts. Imagine standing in an elevator. Suddenly, you start floating. Have you entered a realm of zero gravity, or is the elevator falling? This is the premise of one of Einstein's most intriguing thought experiments, often referred to as the elevator experiment. In this mental exercise, Einstein dives headfirst into the complex world of gravity and inertia, challenging our perception of these fundamental forces. To understand this better, let's delve into the heart of the experiment. Einstein asks us to consider two scenarios. In the first, you're standing in an elevator in outer space, far from any celestial bodies and their gravitational pulls. Suddenly, the elevator starts accelerating upward. You feel a force pushing you down, almost as if gravity exists within this isolated elevator. Now consider a second scenario. You're standing in the same elevator, but this time it's free-falling towards Earth. As it falls, you start to float, seemingly experiencing zero gravity. But are you really in a zero-gravity environment, or just falling at the same rate as the elevator? This, in essence, is Einstein's elevator experiment. He proposed that there's no physical experiment you could perform to distinguish between these two scenarios. This formed the basis for his concept of the equivalence principle, which states that gravitational and inertial mass are indistinguishable. This thought experiment was a stepping stone to his general theory of relativity, which fundamentally altered our understanding of gravity. It proposed that gravity is not a force pulling objects downwards, but the bending of space and time around massive objects. Einstein's elevator experiment challenged our perception of gravity, forcing us to rethink our understanding of the universe's fundamental forces. It showed us that our experience of gravity could be the result of our relative motion, or the curvature of space-time around us. So, whether you're free-falling in an elevator or floating in space, to Einstein, it's all relative. What if we told you that time could slow down? Sounds like science fiction, right? Not to Einstein. Let's dive into one of Einstein's most mind-bending thought experiments, the twin paradox. Imagine two twins. One stays on Earth while the other embarks on a high-speed journey into space. Now, here comes the paradox. According to Einstein's special theory of relativity, the traveling twin would age slower than the twin who remains on Earth. But how can this be? To understand this, we need to delve into the concept of time dilation, one of the cornerstones of Einstein's theory. Time dilation suggests that time ticks slower for an object in motion compared to one at rest. So, in our thought experiment, the twin traveling at high speed in the spaceship experiences time at a slower pace than the twin on Earth. Now you might ask, why would time slow down? It's quite simple, really. Einstein theorized that the speed of light is constant for all observers, no matter their state of motion or rest. This means that if you're moving at high speeds near the speed of light, time must slow down for light to keep its constant speed. So, in our twin scenario, as the spaceship twin zips through the vastness of space at near light speed, his clock ticks slower. When he returns to Earth, he finds his Earthbound twin has aged more. It's as if he's traveled into the future. But remember, this isn't just a cool science fiction plot. The twin paradox has been tested and confirmed with precise atomic clocks on board GPS satellites and with fast-moving particles in accelerators. It's real science, and it's nothing short of astonishing. So, if you've ever wished for more time, a trip at near light speed might just be your answer, according to Einstein. Can gravity bend light? This was another question Einstein sought to answer. Let's take a dive into his mind to understand how he approached this puzzling question. Einstein pondered about a beam of light passing close to a massive object. In his thought experiment, he imagined a star emitting a ray of light and another massive celestial body, like a planet or another star, positioned along the path of this light. According to his theory of general relativity, the gravitational field of the massive object would warp the surrounding spacetime, causing the light to travel along a curved path. Rather than moving in a straight line, the light would appear to bend around the massive object. Now, this idea was quite revolutionary. Until then, light was regarded as immune to gravity's influence, moving along straight paths at constant speeds. But Einstein's theory proposed that light could indeed be affected by gravity, a prediction that seemed to defy common sense. This thought experiment led Einstein to predict a phenomenon we now call gravitational lensing. This occurs when a massive object bends the light from a distant source, magnifying it and creating multiple images. It's as if the massive object acts as a cosmic lens, distorting the light that passes near it. Gravitational lensing was a bold prediction, but Einstein was confident in his theory. His conviction was rewarded in the year 1919, when a British expedition led by Arthur Eddington observed the bending of starlight around the sun during a solar eclipse. This observation was in perfect alignment with Einstein's predictions, providing compelling evidence for his general theory of relativity. Einstein's thought experiment about the bending of light not only reshaped our understanding of light and gravity, but also opened up new ways for us to observe and understand the universe. His predictions continue to be validated as we detect gravitational lensing across the cosmos. Thanks to Einstein, we now know that even light isn't immune to gravity's pull. Imagine observing two simultaneous lightning strikes from a moving train. Would they still appear simultaneous to a stationary observer? This question sets the stage for another of Einstein's thought experiments, known as the train experiment. Einstein invites us to picture a train moving at a constant speed. Along the track, at equal distances from the train, two lightning strikes occur simultaneously. As a passenger in the middle of the train, you witness these strikes at the same time because the light from each strike reaches you simultaneously. This is due to your position equidistant from each strike. But what about an observer standing on the platform as the train speeds by? To them, the lightning strike at the front of the train appears to happen first. Why? Because the light from that strike doesn't have as far to travel to reach them since the train is moving towards it. The light from the strike at the back of the train, on the other hand, seems to happen later, because it has to catch up to the observer due to the train's forward motion. Here, Einstein is challenging our understanding of simultaneity, the idea that events occurring at the same time for one observer should also occur simultaneously for all observers. But as we can see from the train experiment, this isn't the case. The concept of simultaneity is relative to the observer. This thought experiment supports Einstein's special theory of relativity, which posits that the laws of physics are the same for all observers in uniform motion relative to one another, and that the speed of light is the same for all observers, regardless of their motion or of the motion of the source of the light. In this seemingly simple scenario, Einstein managed to shake the very foundations of our understanding of time and simultaneity. He showed us that time isn't a fixed, absolute entity, but something flexible and relative to the observer. Einstein showed us that even something as seemingly absolute as time could be relative. These thought experiments are just a glimpse into the brilliant mind of Albert Einstein, a mind that dared to question the very fabric of reality and in doing so, forever shaped our understanding of the universe. Let's take a quick recap. In the elevator experiment, Einstein challenged our notion of gravity, positing that we cannot distinguish between the effects of gravity and acceleration. The twin paradox, on the other hand, unraveled the mysteries of time dilation, a cornerstone of special relativity that shows time can speed up or slow down depending on how fast you're moving. The bending of light experiment brought forth the revolutionary idea that light's path is not always straight, but can curve in the presence of massive objects. This formed the basis for gravitational lensing, a phenomenon that astronomers use today to study distant galaxies. And lastly, the train experiment, a thought-provoking exploration of simultaneity, showed us that events happening now for one observer might not be happening now for another. This concept is now fundamental to our understanding of space and time. Einstein's thought experiments were not mere intellectual musings. They were revolutionary ideas that pushed the boundaries of human knowledge and continue to shape modern physics. In the realm of thought experiments, Einstein was an unrivaled explorer, forever changing how we perceive the universe. So next time you're in an elevator or watching a lightning storm, remember, to Einstein, it's all relative.